Okay, let's take a big picture view of kinematics and then break it down to even doing some math with some of the equations that we have in our biomechanical toolbox. So we are in the branch of mechanics referred to as kinematics, the study of motion without regards to the forces causing that motion. The study of motion without concern of forces causing motion. Now, our next section we will do, we will concern ourselves with forces causing motion. And really what we're working towards is Newton's second law, where we'll have kinetics, the study of forces causing movement, and the A is the kinematics. And obviously these two things go together. These two branch of mechanics go together. All right, but we are in kinematics. And remember, there's three types of motions. Change pens here. Types of motion. We have linear. All points of an object travel the same distance. And remember, we have rectilinear. The object travels in a straight line, and curvilinear. Curvilinear, it travels along a curved path. So we have the object going like this, time one, time two, time three, time four, and all points of the object travel the same distance. The line, the dotted line would be the same length. In curvilinear, we simply keep the same orientation of that object, oops, as it moves along a curved path. And if we trace those lines, we would actually find that they're the same exact distance. So all points of the object travel the same distance. The second type of motion is angular, or I say angular and I start writing it, and then rotational. And this is movement about an axis of rotation. So if this is time one, and we rotate this object over to somewhere else, time two. So we have our axis of rotation, and the object rotates around that axis. All right, and then the third type of motion is general motion, and this is the majority of human movement, and it is simply a combination of linear, either rectilinear or curvilinear, and rotational. Now, really, we want to get to understanding general motion. And what we do to get there is we'll do a linear analysis, then we'll do a rotational analysis, and then we'll put those two analyses together to ultimately understand general motion. The other thing to remember in setting up kinematics, we do need a reference frame. And we, in this class, will be using pretty much a Cartesian coordinate system, three axes at 90 degrees to each other. And what we can do is then track an object in space at different moments in time, T1, T2, T3, T4, and we can track the X, Y, Z coordinates, X4, Y4, Z4, and over here would be X1, Y1, Z1, and obviously X2, X3, X4, so forth. All right, we can track the X, Y, and Z coordinates, and then we can start describing the change in position. Now this is, I've drawn a single point, so this would be something that we would start off with linear, but it could also be something that is rotating as well, and we would look at the rotational movement as well. All right, so now let's talk about our kinematic parameters. And and what I'm going to do is I'm actually going to write two columns here. I'm going to put linear and angular kinematic parameters. And I'm going to start with position. And we have distance and displacement. Distance, total change in position. Scalar, units are any units of length. Displacement, straight line distance between 2 points. And we use the equation delta S equals SF, final position minus initial position. Units, length, meters, yards, whoops, what have you. All right, vector, scalar. Now on the angular world, we have angular. Distance, total change of rotation, and I'll draw this one here. If we have the object here at this point, I'll do T1, sorry, and then I have the object, I'm going to just draw it here first, and I'll show you the rotation here at T2, and maybe the object goes all the way around and back around. We would actually track that total change in position. So we do a whole circle, a whole rotation would be 360 degrees, then plus whatever this is here. All right, so total change in angular distance, which is analogous to linear distance. And then we have angular displacement, which we'll use delta theta equals final position minus initial position. And then we actually are looking for the change, it's like the straight line distance, but just the quick change in position of the object that's rotating, and we're not going over 1. So angular displacement will always be less than 360 degrees. And the units here, we do have our options here. We can use degrees, which you're probably mostly familiar with. Radians, which is a very good set of units to use when we use angular position, velocity, or acceleration outside of just PVA. And then the third one, which is really for angular distance, is revolutions. 1.5 somersaults, 2.5 somersaults, what have you. Okay, so that's position, both the linear and the angular. Then the next parameter is velocity. Oh, I'll do, velocity. The time rate of change of displacement. And we use the equation V equals delta S over delta T, SF minus SI over TF minus TI. In units, or any units of length over any units of time. And the term that we also try to tap into our knowledge of that's closely associated with this is speed. And if I'm in a physics class, I may actually define the magnitude of the velocity vector as speed. That works, but in biomechanics, we typically use speed to represent the time rate of change of distance, which is a scalar, and this is a scalar, velocity is a vector, and displacement's a vector. We'll actually find that there's more use in using vectors as we get deeper and deeper into biomechanics. And so we're going to focus in on velocity and displacement. On the angular side, we have angular velocity, and we use the sign omega is the time rate of change of angular displacement. So delta theta over delta t, final minus initial theta divided by the change in time. In the units being any units of angular displacement, so I'll do e.g. degrees per second, radians per second, and so forth. Angular speed would be analogous to linear speed, and that would be distance over time, angular distance over time, same set of units, scalar, 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 and a scalar, vector, 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 vector. Remember, vector, we do need to be careful with our math, and there are some rules that we need to follow, and the direction of the vector is part of the description of the parameter. Vectors are described by magnitude and direction. Okay, our last parameter is acceleration. Time rate of change of velocity, how fast velocity is changing. And that equation is A equals delta V over delta T, VF minus VI over TF, oops, it's DF, minus TI. And units, any units of velocity, for example, meters per second, over any units of time, seconds. And remember, this is the same as meters per second squared. You probably are used to seeing acceleration units presented like that. I don't use a scalar of acceleration, but acceleration is a vector, and it's described by both magnitude and direction. And on the angular side of the world, we have angular acceleration. We'll use the equation alpha equals time rate of change of angular velocity, delta omega over delta t, final minus initial angular velocity divided by the change in time. Units are any units of angular velocity over any units of time, which would be the same as degrees per second squared, degrees per second, what have you. Any units of velocity, and this is an EG over here too, EG. Okay, so those are our kinematic equations that are in our biomechanical toolbox. Angular acceleration, linear acceleration, angular velocity, linear velocity, angular displacement, linear displacement, distance, angular distance, speed, angular speed. So now, you just want to rote memorize these parameters and the equations that go along with each one of them. But you also want to eventually be able to get to a point where you use them. And just like a toolbox that has tools, there's times that you're going to pull out one of these equations, and that's the appropriate equation to use for the job that you're doing. So let's throw a few questions in, and let's just do a couple of math problems. And although I present that biomechanics is not a math class, there are times that we just need to do math. So let's do a couple of problems, and I think you'll get the sense of how this would go. I could create a word problem that would describe different parameters, and you would need to use those parameters to solve for a particular another particular parameter. So let's do one where someone is running, and they're running initially, I'm not going to write out the whole problem, running initially at 3 meters per second. And then let's say they they start to slow down and they stop. And the time that they stop over, I'm going to do this so it's easy math, it takes me about 6 seconds. Okay? And the question then becomes is what was the acceleration over that time period? So remember, when doing word problems, there would be a word problem listed up here. You would write out all the parameters you know. You'd write down what you don't know. Then the next step is to put an equation down that has all but one parameter, that one parameter being the one that you want to solve for. So in this case, we want to solve for acceleration. And you just look at all your equations and say, which one has acceleration in it? Or right now, the only equation we have is this one right now that has acceleration in it. Now, as we get deeper into the course, we'll have some other equations. And so your task will often be to pick out the correct equation. And once you have the correct equation, then it's just a matter of doing math. And so in this case, the equation is acceleration delta v over delta t, final velocity minus initial velocity divided by the change in time. Let's see if we have everything but one parameter. I don't know A, so I'm going to circle that. I'll put a little question mark right there. Do I know VF? Yes, I do. I was given that. That's going to be 0. I'll put a little check mark there. Do I know VI? Yes. Do I know TF? Well, I don't know TF, but I know delta T collectively, so I can put a check mark there. I've got check marks over everything except one parameter. That means I can solve for that parameter. If I have two things circled, that means that I did not pick the right equation, or ultimately you need two equations, two different equations to be able to solve the problem. In this case, I've got one parameter unknown. I know everything else. Now I can really claim victory at that point. Now it's just a matter of putting the numbers in. So VF is 0 meters per second minus VI, 3 meters per second. And I keep my units with the parameters as I put them in, and obviously keep the direction. And then the delta T is 6 seconds. That's 0 minus 3, so that's negative 3 meters per second divided by 6 seconds. And that is negative 1/2 meter per second, which we know as negative 1/2 meter per second squared. So 0.5, negative 0.5 meters per second squared. And if you don't remember this, meters per second divided by seconds, I make this a fraction, negative, or let's go over 1. And that's the same as meters per second times the inverse of the denominator. So 1, you flip it over s, and you get meters per second squared. Okay. All right, not bad, right? Well, let's change the problem. Maybe I give you a problem where I say this object is undergoing an acceleration of 2 meters per second squared. And don't get thrown by the negative sign. All that means is, well, let me back up, sorry. This negative sign, all that means that's going to tell us the slope of the velocity versus time plot. So in fact, I could do this another way. I could plot velocity versus time, positive, negative, and 0. And I start with a positive 3 meters per second, and I end with a 0 at 6 seconds later. 1, 2, 3, 4, 5, 6. I do that right. I can connect the dots. The slope of that is negative, which we already know is going to tell us that acceleration is going to be negative. So that's a good check. And the steepness of that slope is 1/2 meter per second over seconds. All right. So our graphing matches up with our calculation. And what would we say is happening? This is slowing down while moving forward because everything's in the positive direction. All right, so let's do another one. Let's say the acceleration is 2 meters per second. And my final velocity is 6 meters per second. And my delta t is 3 seconds. What is my initial velocity? Well, now all I need to do next is pick an equation that has VI in it, VF, delta T, and A. I go through my equations, and again, I come back to this one right here. All right, so let's put the equation down. A equals delta V over delta T, VF minus VI over TF minus TI. What do I know? I know A, I know VF, I know delta T collectively, and I don't know VI. So now I got to solve for VI. Now I don't plug my numbers in yet. What I do is I rearrange this equation so that VI is all by itself on, I like to put it on the left hand side of the equality sign. So let's do that. So let's move TF, let's move delta T over to this side of the equation. That equals VF minus VI. Remember, whatever I do to this side of the equality sign, I have to do the same thing to the other side. So if I multiply this by delta T, that would cancel that out. And I have to multiply by delta T over here. So I get A delta T equals the numerator, VF minus VI. Now, I might as well move VI over here because it's a negative over here. So I'm going to add VI here. I'm going to have to add VI over here. So I get VI plus A delta T equals VF. I'm almost there. Now I need to move A delta T over to this side of the equality sign. So I'm going to subtract A delta T, which means I'm going to subtract A delta T from this side. So now I end up with VI equals VF minus A delta T. Perfect. Now I have my one parameter I don't know over here, and I have all my other parameters over here. This is victory. All right, now it's just a matter of plugging the numbers in. So VI equals VF, 6 meters per second, minus acceleration, which is 2 meters per second squared, times time, which is 3 seconds. Keep that in parentheses to make that easier to see. So now I'll just do this out. 6 meters per second minus 2 times 3 is 6 meters times meters per second squared times seconds. Let me do a quick unit analysis. Meters per second squared times seconds. Hopefully you see that cancels that, and I end up with 6 meters per second, which means I have 0 meters per second. And oh yeah, that's right. Okay, I was just checking my brain froze there for a second. I am solving for VI. VI. All right, good. All right, let's see if this makes sense. And that's what I was just doing in my brain. I'm going to graph it out again. I really like graphing. Velocity here plus minus 0 time. And now my initial velocity I solve for is 0. And my final velocity is 6 meters per second. So I go up here to 6 and I go over here. And that happened 3 seconds later. Let me do, this is 1, 2, 3 seconds. 1, 2, 3, 4, 5, 6. So it's 3 seconds later. There's my other dot. I'm going to do that. All right, now that should be a positive acceleration, which it is. Oops. It's given as plus 2 meters per second squared. So this all makes sense. So my initial velocity being 0, my final velocity being 6 meters per second, and that happened over 3 seconds. And that acceleration, the slope of that line is 2 meters per second squared. All right, so the graphing and the math all go together. There's no trick with that at all. And some of you may gravitate towards using the graph, and some of you may gravitate towards using numbers. Either is fine. If you're given this in a question, you can actually generate numbers to then do the math. Or if you're given the numbers, you can actually sketch out a quick graph to see if you're okay. All right, so now you can see that really what we would do here, or what I would do, is I would start testing if you know these equations by giving you a word problem and giving you all but one parameter and then solving for that parameter. So let's look at angular velocity. The angular world, and I gave you a word problem on something involving angular velocity, angular displacement, in angular time, realize that there are, in essence, at least 5 questions I can ask where I can ask you to solve for one of these parameters and give you all the other parameters. And so what's good practice is to try to rewrite rewrite this equation 5 times with each of these parameters by itself on the left-hand side of the equality sign. So for example, if I wanted to solve for, let's say, solve for theta f. All right, so I could give you all the other parameters and say, what was theta f if everything else was known? Theta I is known, Tf and Ti are known, and omega is known. Well, now we just need to rewrite this equation so theta f is all by itself. And I could do it a little quicker this time. We can do omega times delta t, Tf minus Ti, equals theta f minus theta I. And then we can add theta I over here. So we have omega Tf minus Ti plus theta I equals theta F. I'll just rewrite it so theta F is by itself on the left-hand side of the equation, omega TF minus TI plus initial position. Now, what we would do next is whatever we knew in terms of the parameters that are given, now I plug them in and I solve for theta F. So you can do that with each of these equations. Alpha equals delta omega over delta t. Practice rewriting this, final minus initial, and you can see it's the same format as the previous equation. So, and as we get deeper into biomechanics, we'll have more equations for alpha, but right now we just have the one. So really the math problems are not that bad. And on a test situation, I'll ask you first, usually, which equation would you use to solve for a particular problem? And then I'll also test whether or not you can use that equation. It's like using a tool in the toolbox by giving you some information and then actually doing the math. But the math is not that bad. And as I did on the previous problems, the math actually lines up nicely with the graphing approach that we've taken in some of the descriptions of the parameters. Okay, I hope that helps at least give you a sense of what the math type questions would be. But again, you got to know your equations. You need to know your units that go along with those equations. Okay, thank you.